Good afternoon, everyone. I'm Omar Oreifej, Director of Computer Vision and Machine Learning at Synaptics. I'll be talking about computer vision techniques for reducing the data collection pain. Synaptics is a semiconductor company. We have multiple products with integrated NPUs. My team in particular focuses on designing solutions for low-power AI at the edge with applications for home, workplace, industrial, mobile, and auto. And we've recently developed CNN models for our latest low-power SoC that's called the Katana. On the right, the top right, you can see the architecture for Katana, and most important part is the NPU, where our CNN models will execute. On the bottom, you can see four models that we designed for Katana. The first one from the left is the overhead person detection. Here, there's a camera mounted on top of a door and capturing images of people while they enter and exit the room. And the neural network model will consume the images and detect the people in them. And this is really used for people counting applications. The second model here is a meter reading model. It's basically based on a camera that's mounted in front of a meter and capturing images of the digits. And the model will consume these images and will detect the location of the digits and will recognize them. So this is really useful for converting an old, outdated, non-smart meter into a smart meter with the connectivity. The third application here is the fallen person detection. Here, the camera is mounted on top of a ceiling and capturing these pictures, and the neural network model is classifying every frame to decide whether there's a fallen person in it or not. So this is really useful for ambient assisted living applications. And finally, here the face detection. Here, the neural network model is detecting the faces up to 7 meters, and this model is really useful for smart home applications. And so in designing these models, so many components need to come together in order to produce a successful CNN models. And I'll be talking about the data component, which is one of the major components. We know that we need thousands of representative examples to produce a successful CNN models. Why? Because the network needs to learn how to generalize to many conditions, backgrounds, scenarios, people, ethnicities, and so on. And well, you can use public databases for that. You can say, oh, I'll go use COCO database or ImageNet and so on. And you can do augmentation and domain adaptation. But that works well for standard computer vision problems. And once you are talking about a specific application, you'll find that they are limited. So for example, for the overhead person detection problem, we said, OK, let's use COCO database. But then you quickly find out, well, there are no overhead images in COCO database. And it's not using our target camera. Our target camera is a cheap, low-power, well, noisy camera. And the images in COCO cover a large spectrum, but very few examples may fit this problem. And so you quickly will realize that, well, we need to collect and annotate. I'm sure you guys are all familiar with that, and that takes a long time and effort. And this talk will highlight some simple techniques that we applied in our neural network development journey to reduce the data collection effort significantly. So I'll go over 4 of them. One is called background blending. So for the overhead person detection application, well, we needed a lot of images of people in a diversity of backgrounds and conditions. So in order to facilitate that, we blended a small amount of annotated images with a large amount of background images, because background images are easy to acquire. And so this is an example. So on the left side, you have an input image. On the right side is a target background image. So our goal is to blend the person with this background. And so simply we take the annotation that we made for that frame, and we create a blending mask, which is centered on that box, and fades out as you move away from the center of the box. And then we just blend the input image and the target background image, and we get an image that looks reasonable. It feels like the person is now in that new environment, the target background image. So with this simple approach, we improved the generalization of the method significantly, actually, and now it works outside of Synaptics offices where all of the training data was collected. All right, so I'll move to the next technique, which is body segmentation. So for the fallen person detection application, we needed images of fallen person, again, in a diverse backgrounds and locations. And so instead of asking people to actually fall on the floor, we asked them to lay on the wall, lay back on the wall, and we segmented the body of the person automatically and produced synthetic fall images. So on the left side here, you can see the original image. This is actually myself leaning against the wall. And we can automatically, with a neural network model that's trained offline, to do the segmentation. And then we cut out the person and place him in any background, desired background that we would like. So that's the third image here, the final synthetic fall image. The last image is a real fall image, so you can see that they are very similar. And so with this approach, we were able to produce a large amount of fall data without actually falling. The third approach is annotation transfer. So in the meter reading application that I mentioned on the first slide, well, we need a large amount of images of meters and corresponding annotations with the digits, 1, 2, 3, and their locations in the image. And in order to facilitate that, we designed an approach that is allowed us to only annotate a reference frame and transfer all the annotations from the reference frame to all of the other frames. So I'll go in the details of that. So initially, you take the meter physically, and you place it on a synthetic background that's rich in texture. And the reason you want a background that's rich in texture is that later we'll be detecting what's called the interest points or feature points, if you're familiar with classical computer vision. And we picked this nice picture, but you can basically design any background that you like. If you want something with synthetic interest points, that works too. And then we send a random digit sequence to the meter, and then take the camera and move it around in different poses and distances, and save that video and the digit sequence as a label for this video. Now, next we need to annotate the digits in the video. Where basically, we need to find the locations of these digits and their label in each frame of that video. So how do we do that? We pick a reference frame from the video and actually annotate it with the digits shown in blue here, and a mask, which is shown in red. All right, this mask determines the region of the digits, so we'll use that later. And then we compute interest points. If you're familiar with SIFT, for example, you can use that, or any other interest points. We compute interest points on the reference image in all of the target frames, right? And based on these we match these interest points between the reference image and every frame. And based on the matching result, the matching is done with a RANSAC algorithm. Based on the matching, you can compute a homography transformation, which you can apply to warp all of the interest points from the reference image to the annotated image. So we can then warp the annotations from the reference frame to the target frame, as well as the mask. And then we can use the mask to remove this synthetic background that we applied and add any desired background that would be representative for your application. So with this approach, the entire data collection and annotation was reduced to a few minutes. Of course, that's after writing the code to do the transfer. All right, so the final approach that I'm going to talk about is called camera mapping. So here in the face detection application, we needed to detect faces using a low resolution camera. And the appearance of this target camera is different from the regular RGB images that you find in public databases. And so instead of collecting training data from the target camera, we decided that we can process the publicly available images to map them to characteristics that make them similar to the target camera. And so these are the operations that we apply. We control the aspect ratio, change the images to grayscale, we change the tone mapping, we add lens distortion, and change the resolution, the sharpness, the noise, and we change the dynamic range. And so this is, on the left side here, you can see an example image from wider face data set, which you can use for training face detection. And then after applying our processing, we get the image on the right. So you can see, for example, the lines, the straight lines on the track are now curved because of the lens distortion model that we apply. So if you use the public data sets directly for doing that facial recognition detection, you will get 73% average precision, but when we apply our technique, we improve that to 79%. In conclusion, we presented techniques that greatly reduced the data collection effort and resources. They enabled us to develop accurate neural network models with short amount of time and deploy them on Katana. And as a next step, we are exploring more advanced synthetic data generation methods. Thank you.